Victoria. I'm a peer leader for Physics 142. We hosted a review session on the 16th from 10 to 12, and I feel so bad that I forgot to click record for the first two beginning questions that I did for you guys in the recording. I understand some kids have work, so they won't be able to watch the actual Zoom, and I feel bad they won't have the same experience by missing half the recording, so I'm going to record this so they can watch both recordings and have the full experience that their classmates also had. And I will try to mimic it as best as I can with the questions other students asked to make sure you guys can study efficiently as well. So we first started the meeting off looking at problem 5 from exam C. So I really like this question because it involves a lot of steps and problem solving you'd see on the exam as well. So just to practice some good testing techniques is whenever you read something, highlight some keywords so that it can give you hints on what to do if you're lost. So here it says the cylinder has a radius of 0.4 meters and a height of 0.8 meters on a non-uniform electric field that exists in the place of this equation here. So this equation works in the j-hat direction or the y direction, and it's dependent on y. What does that mean in terms of what we see here? Well, if you look, that means when you're down here at y equals 0, right? Since we know it's all going to be in the y-hat direction, so it's going to be somehow up in the y, it's going to be positive, then we know at y equals 0, there's going to be nothing, right? There's going to be no. But then as you go up and up, right, it's going to be a little more, a little more, a little more, and a little more, the more you go up. So, and it will continue going through. So that's just a way to visualize what this equation is here saying, and it's always good to draw a picture as you go by. So now it says here, for the first question, calculate the electric flux through the top, bottom, and side. So this question kind of gives you hints as you go. The first thing I want you to do is, hey, whenever you see this keyword of electric flux, or you hear the words like Gaussian, or just flux in general, right? I want you to think automatically to these two equations. So on your equation sheets, you're going to see the equation for flux, right? You're going to see this one here, and this one here. So automatically when you read a flux or Gaussian, think of these two because you're either going to use one of these equations or two of them combined. Always, whenever you see those two keywords, right? So here, knowing that those are the equation we'll use, it's saying, hey, really, just calculate the flux for the top, the bottom, and side surfaces. Now, the two main differences between these two equations is that this one here relates to the Gaussian surface you're making, right? This is the surface integral, especially if it has that little dot there. This is the surface integral of the Gaussian. You're looking at the E through those surfaces. This equation, the Gauss's law, looks at what's inside the surface you made, right? It's looking at what's inside. So while this one references the Gaussian surface, this one represents only what's inside, right? Like what's the charges you're working with inside. So these are the main differences in these problems. A lot of kids, when they come into office hours, they go, hey, it said area here. And when we had questions where you had like a charged cylinder, right? And then your Gaussian surface was encapsulating it, a lot of kids would be like, hey, your area, how do you know you're not using the area of this, right? Your charged surface. Why are you using the Gaussian surface? Why? Because this equation talks about referencing your Gaussian surface, and this references your charged surface. So when you're looking at area here, you'd only do the Gaussian surface area, if that helps a little more. That's the biggest question I get when people come into office hours. Knowing that this question we're looking at specifically is asking through surfaces, we're going to do this equation. Why? Because one, it's referencing flux. It says it in the equation itself. And also two, because this is doing the surface integral. So perfect. We're going to use specifically this equation. We're saying I flux is equal to the integral of E dot dA. And we're doing that for the top, the bottom, and the side. Let's first look at the top. So if we're looking at the integral for the top, right, we're saying top here. This is the integral of E dot dA. So if we look at the top, let's draw a little picture here. We look at the top, we know that, hey, this integral, we're looking at the full, E is constant, right? It's constant throughout the whole, well, at least the level you're at, right? So if you're looking at the top, the top is always at the same level y. So E is going to be constant. And A is also constant, right? It's a constant surface. Nothing's changing. So really, you could just look at this alone as E dot dA, since you know these variables are consistent throughout the whole surface on its own. And we know that E dot dA is also equal to E times A times cosine of the angle. Whenever you write variables, it's important to identify what each one is. So E, the electric field from this equation. We have A, which is just the area of a circle, right, from the top part. And then cosine of a specific angle. The angle is between the normal direction of the area and E. This is important because people often say, how do you know the angle is not different? Well, the angle is identified through these two components. So if you look at this shape, we're going to want the normal direction of area, which is here. Another very common question I get is asking, hey, so normal means perpendicular, right? We have the perpendicular surface. So it could be this is perpendicular, but also this is perpendicular. So a lot of kids ask me, hey, why are you choosing this top one and not downwards? Because both of them are 90 degrees to the surface, but why are you doing that? Well, we want a specific vector pointing out of the surface, right? Normal out of the Gaussian shape you're making. So if we did down, you're inside the Gaussian surface. That's not what we want. We want out of perpendicular, out of the surface itself. That's why we're using this one here. Now we're doing the normal direction, the angle between the area and normal direction. So this is the normal area vector, and the E. Right? So we already said that, hey, E is only in the y direction, this j direction. So if I use blue for E here, it would look something like this, right? You have something going up, right? It would actually be everywhere around here, but with this normal hat, how would the angle be? Well, the angle is 0. Oh my goodness. Angle is 0. So if you do cosine of 0, what is that equal to? That's equal to 1. Now, oftentimes, I always forget, or I was one when I'm nervous in class. I'm always like, oh, on that exam, I don't know what cosine of his angle is. Always draw pictures, do what helps you, okay? So here's a unit circle. Here's the origin, right? If you're at 0 degrees, you're right here, right? What is x? Cosine talks about the x component. So what's the x component here? Well, x component is 1. So that will help you, if you draw a little circle, that will help you see where your x could be, right? Or what your x value is, it's 1. So cosine of 0 degrees is 1. So now if we go back to this equation again, we know, hey, it's E times A times cosine of the angle. Our E is given through an equation, right? So we have 800 times the y variable plus 200. And then your A is, well, of this surface. This is a circle, right? So area of a circle is 2 pi. Sorry, not 2. Pi r squared. Now this is kind of plug and chug, right? Well, now I don't know what y is. I don't know what r is. Why? Because it's representative of where this surface is and what it is, right? So, or what and the qualities of this circle, right? So the quality of the circle, it gives it to us, right? R is 0.4 meters. And then the placement of this top surface is, it's really nice that they give you a coordinate system here because this identifies y as 0. So if you go up, this one is at the height of the cylinder itself, so that means y is equal to what it says right here, right? Same thing as the length, 0.2 meters. So now we just plug and chug as we go, right? So now we know this is 0.8. And if you put that in your calculator, you're going to get a flux through the top surface of 422.2 newtons per column meter squared. So we already have it for the top surface, right? Flux through top surface. Now we have to do the same thing with bottom and side, and hopefully we can do this a little quicker now that we understand the basic properties happening in this first equation. So now let's look at the bottom one. So that's going to be E dot dA. Again, for this bottom surface, E is going to be constant. Why? Because you're at a constant fixed y. And then A, well, area is not changing, right? So you could just consider this just E dot dA. You don't need that integral. Now this you can convert from EA cosine of the angle. Let's look at the shape itself to identify what this angle is. I usually like doing the angle first because sometimes it makes your whole equation sometimes pointless, right? There's no need to do the integral if it's 0. So this is usually a defining factor on if it's positive, negative, or 0, right? So let's do that now with the bottom surface. We want the normal vector to go out, right? So out would mean that it's perpendicular and down. So here, if I drew it perpendicular and down, and then if we redraw what our E is, well, E is here, E at 0, right? You can either take this two ways. We know that E at 0 is going to equal, so E at 0, we know that it's going to be here. It's going to quantify this as 0, and this is just 200, right? So it's just 200. Sometimes it's, depending on the variables, it could just be 800 times Y, and that's like, there's no variable here. That would just mean it's 0. But in this case, E does have a quantity at Y equals 0, right? And we know that it's up in the Y hat direction. So what's the difference in angles here? Well, this would have, the angle between them is 180 equals theta. So cosine of 180, if you forget what it is, let's draw a little unit circle. 180 is right here. What is that x coordinate? Well, that's -1. So this is equal to -1. Let's plug in everything else we know. We know this cosine is equal to -1. Let's plug in everything else. So again, this is just an equation, right? E is equal to 800 y plus 200. In area, well, the two sides of the top and bottom have the same area, right? Pi r squared. Like we said, we already know the r. It's r.4 meters. And this y is, well, let's look at the coordinate system they give us, right? This y is at y equals 0. So now let's just say 0 here. That's going to completely get out of this 0. So now we're just doing 200 times the area, and that will give us a quantity of flux through the bottom surface of, oh, I forgot to put that negative there, see? I probably shouldn't have put that there. So that negative 100.5 Newton column meter squared. And this is the flux through the bottom surface. Now let's look at the curve. So we have the integral E dot dA. We already established, hey, you could just say it's E dot dA, no integral. You could say E a cosine of the angle between the narrow hat direction and the E. And then you're gonna, now let's look at what the angle between them is, right? Because this is the defining factor most of the time. So I always find this really hard to think about in my head because I'm like, oh, right here it's going this way, or it's just hard for me to visualize it. So sometimes if you come to my office hours, you're gonna see me do a little dance so that you can remember this, okay? So a cylinder, if you think about it, you can almost think of the normal direction coming completely out, right? So I often tell them, say, hey, grab your little brother, grab your little sister, make them do the T-pose, right? This is their little T-pose. Because this is coming perpendicular out of their body, right? Out of their cylinder body. This is the perpendicular coming out of the surface. If you're having a hard time visualizing how that looks around the whole surface, ask your little brother, ask your little sister to spin around. And their hands are gonna simulate how the normal vector will be all around the cylinder. That's important because some kids have a hard time understanding, hey, that's a normal direction. So around the surface, remember, because this equation talks about the Gaussian surface. So coming out of the Gaussian surface is that our E is going up, right? It's like our head, it's going up. So what is the angle between just this up and then your perpendicular? Well, around your arms, your head to your arms are always going to be 90, even if you spin around, right? So that means your angle is equal to 90 degrees. Cosine of 90 is what? Well, let's draw a little thing. Here's 90. Well, our x-coordinate here of 90 is equal to 0, right? This is the x-plane, this is the y-plane. So if our x is 0, that means cosine of 90 is equal to 0. Well, then you're doing, essentially here, you're saying E times A times 0, which always is equal to 0. So through your curved surface, your flux is equal to 0. Why? Because the angle between the normal and the normal direction, the red coming out, and your E is going to be 90 degrees. So now you did exactly what A said. It said find the flux through top, bottom, and side. Just for reference, if you wanted to find the full flux, what we would do is that you would add all these together, and that's the flux of going through that shape, right? That surface. I had someone ask me when in the meeting, hey, when is E.EA equal to EA cosine of theta, and when is it not? Well, sometimes technically it's always equal to this. Always. It's just depending on the problem. Is it going to be easier to define it by angle, or because a lot of people just skip steps because they're here like, oh, I know this is already with it, so it's 1. Like it's parallel and in direction with it, so it's 1. Or it's parallel and opposite, so it's -1. So this is always the case for E.EA is always going to equal EA cosine theta. The question is can you drop the integral, and that's the main question, right? Besides that, this is always true. A lot of people just skip the step if they already know, hey, it's perpendicular in angle, so it's 1, or they already know it's 0 because it is 90 degrees between them. But just a reference in case you had the same question, this is always going to be true, the case between this and this one. And that's not on the equation sheet. Unfortunately, on the equation sheet, they just say, hey, this. So it's up to you just to remember that little step of when you do the dot product between stuff, you're essentially also just doing this because you're taking it in the normal direction, right? Taking in consideration the normal vector. Okay, so after we did this problem, we went on to B because people also had questions about B. Now, B asked for specifically let's read it and do some keyword search, calculate the total amount of charge inside the cylinder. So if you remember when we were speaking before, I said as soon as you hear the words Gaussian or flux or anything, I want you to keep in mind the two equations. I want you to keep in mind this equation or this equation because you're always going to use one or both combined. Keeping that in mind, right, we know that here you're giving flux is equal to this, and here you're saying that flux is equal to this. So essentially, if I rewrite these equations, right, do you guys agree with me saying that, hey, if I solve for one of these equations, and I know the fluxes are the same because same variable, right, they're the same, can you just put them equal to each other? And because they're the same thing, right? So you could also just say, hey, E.dA is equal to Q enclosed over epsilon naught, right? So if you could solve for one, you could solve for the other because they're equal. You could set them equal to each other. Now this little circle thing, remember it's taking consideration each entire surface, right? So for this cylinder, we had three surfaces. We had the curved, we have the top, we have the bottom. And lucky us, question A asked us to find the flux through each side, right? Each surface. So the full surface integral would just be the summation of all these integrals of the top integral, bottom integral, and curved integral. So it would be the same thing as saying the top plus the bottom plus the curve. And lucky us, we did that. And that is supposed to equal to our Q enclosed over epsilon naught. So now we could plug and chug the values we had before, right? So now we're saying, hey, I know that the top is equal to 422.2 plus that negative 100.5 plus 0 for the curved surface is equal to your Q enclosed over epsilon naught. We only want Q enclosed here. They have the total amount of charge inside. So let's multiply epsilon naught on both sides. So essentially you're getting, hey, Q enclosed is equal to epsilon naught, which if you ever forget the value of epsilon naught, it's on your equation sheet. Let me help you guys find it. I think the one best, not the best studying tip, but a very good studying tip is to study all the time with this equation sheet, because half the battle, especially when you're scared on a test, is finding out where stuff is. So if you don't know where anything is, you're going to be more scared, you're going to be more frantic, and you're going to be more lost. If you know where stuff is, you're going to be able to kind of problem solve stuff, be able to make your eyes trace to where you know the general area is, and you'll be good for the exam. So if you don't know where it is, it's right there. So we have E times those two fluxes summed, or the epsilon naught, not E. So that's 8.85 times 10 to the negative 12 times exactly what I put in here. So we have Q enclosed is equal now 2.85 times 10 to the negative 9 coulombs. Okay, perfect. Now, at this point, when we are in the Zoom call here, I'll zoom out so you can look at the full picture. We're in the Zoom call. People are asking, okay, so you're using dA here. How does this change? And then we start talking about, hey, linear density and all that stuff. So they asked, like, how do you know when to use linear density for dq and not other stuff? So I want to highlight back to here the equation sheet, because they don't say specifically what dq can equal to, but they do give you a very large hint right here. So they say charge density can be associated with your linear density, which the units are here, your surface density, which your units are here, or your volume, or your units are here. So when you're given different types of objects, so let me make a new page and just make a new object here, right? Essentially, you're given like a field or a, you're given like a field coming out of a line, of a surface, or of a actual 3D object, right? Or an actual three-dimensional shape. This will give you a hint on what type are you going to use. Are you going to use your charge, your dq? Are you going to associate it with lambda? Are you going to associate it with your surface area density? Or are you going to associate it with your volume density? Well, this will give you a very clear sign of what you're going to associate it to, right? Because if you're doing with a line or a line curved, you're going to deal with your linear, right? Or if you're dealing with a surface, you're going to deal with your area surface density, or 3D is going to be this one. So that will kind of correlate to what you have. Now, they don't give you the exact equation for what dq is equal to according to these three associations. They just say, hey, it could be associated to this. But you can derive it easily with the units they give you here. So the units for lambda, or the linear density, is coulombs over meters, right? Or you could just say this is your charge over some distance, right? Meters is a form of distance, so let's just put L for distance. How would you, so you know dq has to be equal to this with something, right? So what are you going to do with this to get q? You're going to multiply it by a length, right? Or you're going to multiply by that little length you're looking at when you move across this line, right? This little tiny length you're looking at as you're moving across the line. So that's, with this logic, you could just say, hey, dq, if it is a line or a line curved, you could say dq is equal to lambda, or q over L, times some distance L, right? So you're just looking at, hey, how do I get columns alone? Well, you have to multiply it by m, so you get columns alone. So that, even though this equation is not given to you on the sheet, this is something you could derive knowing, hey, lambda is in terms of columns per meter, or charge per length. You just multiply by a length to get your dq, or just get q alone, right? Same idea with these, right? So you have here, they tell you this surface density, it has units of columns over meter squared, right? Well, meter squared is units for what? Well, it's units for area, right? Or you could just say, hey, this is q over area. What are you going to do to get rid of area? Well, you're going to multiply it by an area so you can get rid of q, can you get q alone. So in this case, you're saying dq, I want to just separate this out. dq is equal to your surface density, or q over a, times that changing area, right? The little area you're looking at as you go across the shape. So this, and then the same idea for this, let me quickly run through because I did the same thing on the Zoom call. Hey, you have your c over, they give you these units right here. They give you these units right here. So I know that's meters cubed. What is meters cubed? Well, that is a unit for volume, right? Or you could say this is just q over volume. How do I get q alone? Well, you have to multiply it by volume. So you could just say dq is equal to your density times the changing volume for that certain value you're looking at. So when you're approaching a problem and you don't know which one to use, are you using this one, or this one, like your friend asked in the Zoom call, you have to identify what the shape is, right? Is it a line or that's curved, or a line that's straight, or a line that's like this? Or is it a surface? Is it going by just area? Or is it an actual three-dimensional shape? Nick mentioned a really good point. He said, hey, some keywords you can look at, or just keys in general, is like sometimes a problem will literally bring up lambda, or will bring up, it will literally bring up lambda, or sigma, or density, or rho. in the problem. So this will give you a hint on, like, hey, I'm probably going to use surface or linear if they're giving this if we're explaining this in the problem. The second thing is wording. So a lot of kids are like, hey, how do I know it's this? If it says something like thin rod, that might confuse you, because technically a rod, even if it's thin, you can find a surface cross-sectional area. But if it mentions thin, you're going to use lambda, right? You're going to use a linear density, just because they're saying thin. Or if they just say line, then you know you're using this. This one will give you an actual shape. So sometimes they'll give you like an actual shape, and they'll tell you, like, hey, the area components, like a sheet or something, and then again this will be like a three-dimensional shape. But this is a specific hint for, hey, if you're dealing with lambda, these are also key lines. If they don't mention lambda alone, these are also key lines that can signify, hey, you're dealing with a linear density. Hopefully that helps. Yes. Okay, so after we did this one, we had a student ask about question 4 of the same thing, of exam C. So let's go right here. This one deals with dielectrics, right? You're putting something in of this capacitor so that it works better, right? 'Cause you want it to have a different ratio for charges or all that good stuff going through the circuit. So again, let's practice some good testing techniques and underline some keywords we see when we read the problem. So this says, hey, you have 2 identical capacitors, empty space between them with the same capacitance. They are connected in parallel to a battery. Without changing anything else, the right capacitor is filled with an insulator with a constant of this. So one thing I want you guys to take account of is whenever they mention parallel, well, in circuits, if they mention parallel, I want your brain to specifically go to the fact that, hey, elements in parallel share voltages. That's why I really like it when you highlight these keywords, because then they're gonna make it obvious to you what things they want you to think about, right? Because the main idea about stuff in parallel is that they share voltages. That's why they're mentioning it. They want you to remember that they share voltages. So that's one thing to keep in mind as you go in mind. As they're in parallel, they share voltages. Some kids, I know that I really struggled this when I took this class, is I would look at this and I'd be like, how do you know they're in parallel? Because parallel means they share nodes, right? Well, if you redraw this, you could just redraw it like this. I'm not going to draw it with the insulator in there right now. But you're essentially saying, hey, this point is like this point, so you could just pull it up, and this point is like this point, so you just pull it down. Now the nodes you're sharing are like this node and this node. So since you could just pull this down, you're saying that this node is the same and this node is the same, right? So they're sharing the same nodes as the 10-volt battery, meaning that, hey, if the difference from here to here is 10, then the difference from here to here have to be 10 because they're the same nodes. So that means that here is also 10 volts. So this is a big idea they wanted you to take out of this, and that's why they mentioned this in front of you. So the keywords are important because they highlight these ideas that will help you a lot. If they don't say it, then you have to, they don't want you to struggle that much on the exam, right? Then if they didn't give it to you, then you would have to stare at this problem and be like, oh, what do I notice about the circuits? Well, they're in parallel. But it's nice they mentioned it to you as a hint. Okay, so let's go into what the question's asking, right? So it says, determine the amount of charge that flows through the battery when the dielectric is inserted. So this wording kind of changed, right? Because as you're going through, right, you're having a constant charge or current going through this entire circuit from here, going down this way, right? And this question is essentially asking, like, okay, you have this current, you have this charge going through, you enter it in. Now how much is going through differently, right? So because current is always constant, they're really just asking for a change. They're asking for more of a change. Ooh, no, my colors. Okay. They're asking for more of a change in Q, right, or charge from, well, changes final minus initial. So the final state, or with the dielectric, minus the Q initial in both these circuits, right? So, or before, right, or initial. In the Zoom I said before, so I'll just say before here too. Before. So now that we know we have to essentially do this, we have to find the Q's going through these, in this one for before and after. So let's look at the before first. So we know that they're in parallel, right? So they don't share the same Q, they only share the V. So the equation for Q, right, you're thinking about, okay, I need to find Q, right? Let's look at the equation sheet. Let's figure out where we can find Q. Well, we're talking about capacitance, right, in this problem. So let's look here, and we see that we actually have an equation for what Q is. Q is equal to C times V. C times V. So we have to take in consideration that, hey, they have two different charges going through here, right? So if I want the full charges going in before the insulator is inserted and after, then I have to consider both of these, right? So you have to say, hey, the total Q before is equal to the Q from capacitance 1 and the Q from capacitance 2. So let's figure these out right now. So Q from 1 is equal to the capacitance of specifically the first one and the voltage. And they give us that here. So C is equal to 4 times 10 to the negative 6 farads times voltage. And this is where the parallel comes in hand, because we know what voltage is, right? It has to be equal to the battery because they're in parallel. So this is equal to 10 volts. What is this in the end? Well, it's 40 times 10 to the negative 6 coulombs. And now let's do Q2. Well, coincidentally, these are the same, right? Because nothing's in here, right? So the normal equation is just CV. So C for 2, specifically, because we want the charge for the second capacitor, times V. Same thing. These lines mean same as above. So this is equal to 40 times 10 to the negative 6 coulombs. Let me write this in because I'm scared you guys will be confused. Times 10 volts. Perfect. So now if we plug these back in to these above, let's plug and chug, right? So this is essentially 2 times 40 times 10 to the negative 6, right? You're just summing these two together. So we have the total before is 80 times 10 to the negative 6. Now we have to find the final, right? The final with a dielectric. So we have final. And just like before, we have two things contributing to the final charge, right? We have the charge from C, capacitor 1, and capacitor 2. So really, our Q final is equal to Q1. Well, this is just regular Q1 because there's nothing in there, right? It's just Q1. Plus, now we have a Q from 2, but this is with a dielectric. Sorry, not with an insulator, right? Insulator inside there. And this is our Q final that we need for this point right here. We need this for this, and this is from here. Well, Q1, lucky us, is going to be the same thing because things don't change, right? C1 V. So I'm just going to write, we already know this is the same, so 4 times 10 to the negative 6 times 10 is equal to 40 times 10 to the negative 6. And now let's do Q2. So Q2 is equal to, well, Q is always equal to C times V, right? But when you add an insulator, you're essentially changing what your C is. So you're saying that C is now equal to K, the dielectric constant, times the original C. So really, if this is the new C with dielectric, right? Because now we're saying this is C with dielectric, because that 2 has a dielectric in there. I always say dielectric, insulator, has this in there. So now we're really saying that this is equal to K times C2 V. Right? So this means original, right? So for C2, the original is just the C2 without anything. So if we're supposed to put this in, K is given to us, right? K is given to right here as 3. So we have 3 times the original capacitance, which was 4 times 10 to the negative 6, times the voltage, which is 10. And we have that equal to, in my head, that is equal to 600, or I apologize, I'm going crazy right now. This is equal to 120 times 10 to the negative 6 coulombs. Again, this is not what we want. We want the final, right? So this is, put them back in here, add them up. What you have is 40 plus 120, so that equals 160. Yeah, 160 times 10 to the negative 6 coulombs. Because I put those back from here. Perfect. Well, this is not the final answer. This is just a highlighted answer. So now we know that, hey, the difference should be the final minus the initial, right? So now we can go back here and say, hey, the final is 160 times 10 to the negative 6 minus 80 times 10 to the negative 6. So our change in Q is equal to specifically 80 times 10 to the negative 6 coulombs. So this is your final answer. The hardest part of this is realizing that they wanted the change in Q, and then realizing, hey, you have to consider both the Q of both capacitors, right? And you could just add those in, right? Because that's the Kirchhoff's current law, where the current in has to be equal to the current out. That's why we have to consider, hey, the current in is both C1 and C2. So, or Q1 and Q2, right? And that's why we have to consider both of them to be the full before and the full after, or the full after. So this is your change in Q. If we approach question part B, it says determine the amount of work required to insert this dielectric. Well, we know work specifically is equal to the change in U, plus or minus, because this will depend on if this is exerted or inputted. Well, this charge is happening almost naturally as it goes through, right? We know that this is inputting more work, right? This dielectric is giving more, right? Because this is increased, right? So we know this is going to be a positive change, right? This is exerted through this process of adding the insulator in there, right? So we know it's going to be positive U. On the equation sheet, it just has negative, but it's up to you to identify, hey, I know that this depends on if it's exerted or like if it's increasing the work or decreasing the work. So this one we know it's going to be positive. So that means that it's going to be U final minus U initial. What is U? That's like your potentials, right? So let's look over here and try to find what U is on our equation sheets. So again, we're dealing with a capacitance problem, so look here, and then look at, hey, we're looking at U's now. So we have all these equations for U. Really, you can use any of these equations. It doesn't matter, you'll get the same answer. Personally, I like to use stuff that was either given or I know for sure is correct. So that's why I like using, I lean towards this one just because they give us the capacitance for both capacitors, and the voltage we know has to be equal to 10. If I made a mistake and identified Q wrong in the first part, then this would make this part wrong. That's why I just lean to this. But really, you won't get that many points off if your Q is wrong from A. So in the end, you can use either or. It's really up to what makes you more comfortable. So let's use that equation where we know U is equal to 1/2 CV squared. So again, we have to consider what's initial and what's final, right? So let's look at our initial states for U initial, right? There is 2 capacitors working initially, right? I want us to think back to our past like work problems or weekly problems where we had like 3 or multiple point charges and they're all doing some potential on each other, right? And the total potential was adding them all, right? You have this one of A and B and adding A and C, or B and C, and all that. You had to find the total potential work, right? Or the whole total potential. Sorry, I'm mixing up my words here. But the same thing applies here, right? We want the total I, so we have to find for initial. So this is equal to U due to capacitance 1 plus U of capacitance 2 in the initial states. So now let's go through and identify all of those in the initial states, right? So let's do U from the capacitance 1 from initial state. So really I could just write this 1I. 1 initial. I don't want to confuse you guys with all this thing. Capacitor 1 initially, capacitor 2 initially. So again, the equation is right here. 1/2 C, we're dealing with the first capacitor, right? So capacitance 1 times the voltage squared. We already know these, they're all constant. In the initial state, it just looks like this, right? There's no insulators inserted into either of them. So this is just equal to 1/2 C, which is 4 times 10 to the negative 6, times that voltage, which because they're in parallel is 10. So that is equal to our trusty dusty 200. Yes, 200 times, because we're dividing by 2, 200 times 10 to the negative 6 joules. Coincidentally, our second capacitor in the initial state will be the same thing, just because there's no dielectric, so we don't have to change this C. It's just normal C, and that C happens to be equal to C1. So again, this is going to be all the same. This means the same. So we have 200 times 10 to the negative 6 joules. So if we input these into what we know is the total initial, we get 2 times 200 times 10 to the negative 6 joules. So that's equal to 400 times 10 to the negative 6 joules. And remember, we want initial minus final, so we also have to find our final state objects. So if we go to final, let's do the same process. We know we have to find the total final. And there's two parts, right? There's two capacitors, this one and this one. So we have to take it from the final state of the first capacitor. So first capacitor from the final state plus the second capacitor in the final state. So let's plug and chug, or let's solve these through. So the first capacitor in the final state, again, it's just going to be 1, 2. C doesn't change when you go into the final state. It's still C1, V squared. So this is actually going to be the same variable. So it's just going to be 400 times 10 to the negative 6 joules. And then U of the second final state is going to be equal to 1/2. And remember, this is with the dielectric, right? So the C is changing. This is C2 with a dielectric, V squared. What the dielectric does is that it does K times the original 2, V squared. So we're going to have this as 1/2, 3 times that dielectric, the capacitor, I apologize, and then the 10 squared. So this is going to be equal to, then, with times by 3, it's going to be equal to 600 times 10 to the negative 6 joules. So we have two things, and we want to insert it back in here, right? So if I sum these here, we have 400 plus 600. So we have that at, oh, sorry, I wrote down 400 here. It's the, shoot. I just looked on my left. I knew it was this. So it's the same variables as here, right? So 200, this is equal to 200, I apologize. I just looked right here and then copy pasted. Really, the variables are the same, C1 here, V, same here. So when you multiply them, you're going to get 200, 10 to the negative 6. So 2 plus 200 plus 600 is going to equal to that 800 times 10 to the negative 6 joules. So now we have our final. Let's do a different color maybe. Final and our initial states. And we know that we have to plug it back into here because that is equal to the amount of work. So we know our work is equal to that change, that final minus initial. So we have 800 times 10 to the negative 6 joules minus the initial 400 times 10 to the negative 6 joules. And very satisfying that it's half of each of the other. We have it as just 400 times 10 to the negative 6 joules for the amount of work required. Okay, perfect. Now this is where I was able to cover until I realized I was not recording. I tried to go over all the questions that other kids asked, but if you were ever confused, please email me or Nick or any of the other peer leaders. We'll be happy to help. And we have our office hours still. Nick has one on Sunday online, and I have one on Monday, so please come in. You can ask any questions on any of the practice exams, and you guys got this. You guys can study this weekend, and you guys are already so much smarter than me. What I see in office hours, you guys are already doing 500 better than what I did when I was in this class. So you guys got this. Good luck, okay?